In this lecture, we are going to talk about all the strategies of testing series, and here it's like a summary. Okay, so you want to observe the series before you really start, say, making your conclusion, or start your, I don't know, proof, or your working, because many cases, whether you are trying to show the series is divergent or the series is convergent, are completely different. It's not like solving equations. Let's go ahead and let's see. You need to pick your strategy, and when you at the moment you pick your strategy, many cases you already know whether you are trying to show is convergent or divergent. Some of them, you sort of can go and see, but in many cases, is you already know. Anyway, let's see. So, most importantly, you observe the series, right? Observe the form, and what form you have will decide, what kind of strategy you are going to use for sure. But to start with, we have the two sort of basic series we constantly compare to, which are the P series, which are essentially the series of powers of n, and then the geometric series, which are the sum of power where the base is fixed but the exponent is n. Okay, for P series, when we write it as reciprocal, so you don't have to deal with negative. So when you have the sigma of 1 over n to the p's power, p is greater than 1, the series is convergent. P is 1 or less, the series is divergent. In particular, sigma 1 over n, this is the harmonic series, that is like where the convergent, the dividing point, right? And that diverges. Geometric series, while you look at the common ratio r, and this one actually, when you see the r's, it's quite obvious. When r has absolute value less than 1, the series is convergent. The absolute value is greater than 1, divergent. And in particular, when r equals 1 or negative 1, again, the series is divergent. But if you see 1 or negative 1, it's very obvious, the series diverges. Then, if you have the series that has a very similar form with P series or geometric series, you're going to use the limit comparison test or just comparison test itself. Well, pretty much what the comparison test tells you is that you can drop some lower terms. Say you have sigma of n squared over 2, you can drop the 2. Okay, and the other thing you can do with comparison test is that when you have sine n or cosine n, you can say the absolute value is less than 1. That's the other place you use comparison test a lot. Then number 4 is really like the thing many of you constantly forget, because you focus on the series so much, you forget that, the series, if the series is convergent, the limit of the terms has to go to 0. So if that's not happening, which means either the limit of an does not exist, or it exists but not 0, the series can't be convergent. So before you start getting into the very complicated, tests, take a look at your limit of an. Does it go to 0? It has to be 0 to, for you to proceed. Otherwise, you can simply claim, okay, the limit is not 0, so the series is divergent. If the series doesn't have a very easy form similar to P series or geometric series, and you do see the limit of an goes to 0, we are going to get into some more complicated tests. Alternating tests, that's pretty much when you are going to you have an, when you have alternating test, probably you do it after the ratio or root test fails, because those are for the absolute value. You are testing whether the series is absolutely convergent, and if that's not happening, you go back to C. When both of them fail, as in L equals 1, okay? And that's where, or that's like the, the boundary case. Then you need to see whether the alternating series test work. And again, this works normally with something like -1 to the nth power times, over n to say a fourth. So pretty much it's like an alternating factor in P series, and P goes between 0 and 1. That's where you normally use the alternating series. Of course, the form can be more complicated, but the idea is you need to show Bn plus 1 is less than Bn, and the limit of Bn goes to 0. Okay, you need these two. Sometimes you need to show Bn plus 1 is less than Bn by showing the derivative is less than 0, which means the function is decreasing. And then we have the ratio and the root test. Both of them are very convenient in the sense, depending on the form, you can easily know if the L is less than 1, then the series is convergent, and if the L is greater than 1, the series is divergent. When L equals 1, the test doesn't work, and that's where you might need to do the alternating series test. Okay, and normally the ratio and the root test work or fail at the same time. So if one of them fails, no need of trying the other one. Go back to either comparison test or the alternating series test, or our final chance, which is the integral test. Pretty much the sum of a function in N and the integral, which represents the sum of function in X, are the same. So if the integral converges, then the series itself also convergent. Let's see some examples. First, here I'm not asking you to do whether the series is absolutely convergent or conditionally convergent or divergent. We just do convergence or divergence. So the first one, I'm having -1 to the nth power, 3 to the n, and n to the 5th power. So, in general, the idea is log n grows slower than n to any power. Okay, this, how do I do it? The limit as n approaches infinity, this, or any power comparing to any number with exponential, these are all 0. Okay, a greater than 1, of course, and p greater than 0. I think that's enough. Okay, so given a series or given the terms, you want to see which is the dominating factor or term when n approaches infinity. So in comparison, the exponential is more significant than the power on the denominator. And so we are going to take absolute value and say, not really absolute value, we are going to take the root test since the numerator is more significant. Limit as n approaches infinity, nth root of absolute value of an. That will be the limit as n approaches infinity, nth root of, actually -1 to the nth power after take absolute value will be dropped. So we don't really need that. Let me use red. That's 1, right? So what you're going to get is the limit as n approaches infinity nth root of 3 to the n, that's 3 over nth root of n to the fifth. And remember the limit of nth root of n in general is 1, so this is 3 over 1, or 1 to the fifth power if you want, but still that's 1. So the root test gives us a 3, which is greater than 1. Well, again, go back to the thing. You are having an exponential series, which is a geometric series of n, where the common ratio is 3. So, of course, that's divergent. So we can conclude that the original series is divergent. Next case, we're having the series of a sum of two terms, 1 over n to the third power plus 1 over 3 to the n. Well, actually, again, comparing both of them, as n approaches infinity, 3 to the n goes to 0 faster, which means actually this term is more important in the sense of it's larger for most of the n. But anyway, a series of sums can be written as sum of series, so you can just do them separately, and pretty much I'm having p equals 3, and that is convergent. And this 1 over 3 to the nth power is 1 to the third power, a third to the nth power. This is r equals a third, which is less than 1, also convergent. When you have two series, both are convergent. When you add them up, the sum is still convergent. So that tells me the original, well, I'll just write an, is convergent. Okay, so here I'm trying to show you. Remember, there are p series and there are geometric series. They are very easy to tell. And also, you can do some of them. Next, number 3, I'm having negative 1 to the nth power n squared over n to the third power. Actually, if you look at it, you take the dominating term, you're having negative 1 to the nth power 1 over n, which is convergent, by the way. So how do you do that? How do you show that? Well, actually observing this way, I'm okay. But if you really are going to show it, you will need to say this is an alternating series. So Bn is n squared minus 1 over n third plus 1. Well, having Bn plus 1 won't be fun, right? You will have n plus 1 squared on numerator and n plus 1 to the third power on the denominator. So instead, I'll go for the derivative of f, which is x squared minus 1 x third plus 1. Well, before that, let's make sure Bn goes to 0. This will be the limit as n approaches infinity, n squared over n third, or 1 over n. That's 0. So we have the limit fine. Now the derivative, that is the denominator squared. Then differentiate the numerator times the denominator minus the derivative of the denominator times the numerator, x squared minus, x squared minus 1. Then I work it out. The denominator is a perfect square. I don't need to worry about it. Numerator, I'm having 2x to the fourth power plus 2x minus 3x to the fourth power plus 3x squared. That is negative x fourth plus 3x squared plus 2x over x third plus 1 squared. Well, actually, when x is small, this thing might be positive, but when x is large enough, where you can 3x squared plus 2x, as long as 3x squared is less than, say, half of x to the fourth power, and 2x is less than half of the x to the fourth power, numerator will be less than 0. So we can easily say that's less than 0 for x greater than 5. Because if you add up the coefficients, that's 3 and 2, right? So 5. And they are at least 1 degree lower than x to the fourth power. It's more than enough. So I take 5. And that means bn plus 1 is less than bn for, again, n greater than 5. Ultimately, it's decreasing. That is good enough to make our alternating series converges. But you did all these to show that is true, but the idea to sort of know what you are going to do is because you are having -1 to the nth root, n to the nth power, then you take the dominating terms n squared over n third. You are sort of having the alternating harmonic series. Well, last example for today, I'm having the sum of n squared e negative n to the third power, and that will be sigma, I don't really need 1 to infinity n squared over e n to the third power. Yes, you can do integral test, but actually you don't have to. It's pretty much what's dominating here, n squared on the top, and this is an exponential on the bottom. The bottom definitely is more important. More affects more later as n approaches infinity, which is an exponential of n. So take nth root. This will be the limit as n approaches infinity, nth root of n squared on top over e n to the third power on the bottom. And I don't know if you can get the denominator right away, so I'm going to write it as n. Well, I'll keep the nth root on the top, but on the denominator I'm going to say 1 over nth power, so that you can see I'm multiplying the exponents to get limit as n approaches infinity, nth root of n squared, which is 1 squared over e n third times 1 over n third times n negative 1 n squared. And as n approaches infinity, this is 1 squared, but on the bottom you have e to infinity over into infinity, which is 1 over infinity, and that is 0, right? So the limit of this thing is less than 1. It's equals 0 less than 1. Equals 0 less than 1. I meant 1. So the whole thing converges. I only did 4 examples where I want to show you how you can observe the terms and make up make the decision what you should do with your own series. And this is really just a summary and review of what we have learned, all the tests, and also it's a place where you are going to try to apply, sort of like you don't know which one you're applying, and you need to decide which to do. Okay, and practice is really important for this test, for this packet. Please try 1 to 4.